All right, and hello everybody. Welcome. I'm glad you're here. We're talking about the human mimicking robot hand, and currently we have it open in Keyshot. Samples is 256, and Keyshot, I like Keyshot because everything is so pretty in Keyshot. This is the original robot hand that I created, made of 2205 alloy stainless steel. Now, this distance from here to here is 4 millimeters. And this is a kind of a channel arrangement. This channel, again, from here to here is 4 millimeters. This looks like maybe 6 or 7 millimeters. That's really small. Now, I wanted the hand to have enough strength, the robot hand, to act as a human hand. So this robot hand is strong enough to grab a metal bar and lift up with 200 pounds of force. And you might say, what? But the way the calculations go is you take the cross-sectional area. This is a very standard mechanical engineering approach. You take the cross-sectional area of this shaft, for example, in inches, and then the cross-sectional area is square inches, and the yield strength of 2205 alloy stainless steel is 50,000 pounds per square inch. So you take the square inches of this shaft and multiply it times 50,000. And this shaft winds up, I think it holds like 100 pounds or maybe 120 pounds. Most of the mechanical discussions state that you can say that that's the tensile strength for pulling on it. The compressive strength is for pushing on it without it distorting. And the compressive strength is 1/2 of the tensile strength. If you wanted to put a bend on it to bend it, again, the strength it has for resistance to bending is 50% of the tensile strength. So you have tensile strength, which is pulling on it, compressive strength, which is pushing on it, bending strength, which is bending it. Shear strength is where you hold one side and go this way, and you hold the other side and go that way, and it shears it off. Again, the shear strength is about 50% of the tensile strength. And in order for the hand to lift up 200 pounds, each one of these fingers has to hold up 50 pounds. And the math says that can be done if it's 2205 alloy stainless steel. And because I think these parts are so small, my decision was the way to put this together was to create individual parts from alloy stainless steel and then bolt them together. And that's the original hand. And this is the same size as a human hand. This is about 3.5 inches. And this distance from here to here is about 2 inches. And the hand itself is 6 to 7 inches long. The wrist would be right there. And these are joints that allow the fingers to move around. So the finger, not only can the finger go back and forth this way, flexion, extension, that's that. But it can go back and forth this way. So if I hold it, see it going towards my middle finger and then going towards my thumb, that's abduction, adduction. This is flexion, extension. So the finger, let's see, I'll point it at, the human finger can do this. All of them can. They can all do it simultaneously and in different ways. The thumb of the human hand can be in front of the palm, or you can swing the thumb all the way out of the way so you can grasp and your thumb is not in the middle. So if you had your thumb over here and you tried to grasp something, you'd be grasping your thumb. But if you you can move your thumb away from your palm, so it's over here like this, and then you can grasp something and your thumb's out of the way. And these hydraulic cylinders, you can put enough pressure. Now, when you take the human hand and it can, I'll get my face out of the way here. Okay, it can push this way and that way with 9 pounds of force. Abduction, adduction. It can push this way and that way with 9 pounds of force using the muscles inside the hand. And that is what these hydraulic cylinders do. Right in here. And they need to generate about 18 pounds of force because it's a 2-to-1 lever. And they can do that if they're 2205 alloy stainless steel. And this is the frame that gives rigidity to it. You can see here that I was just showing off. Now, these joints allow, okay, this, compared to this joint, this can go that way and it can go that way. But it can also go at the same time. It can go this way and it can go that way. That's 90 degrees of rotation. All of the axes of rotation are available because of the use of this joint, which I thought was a cardanic joint, but I went to Google and I was wrong. I've been wrong before. It's not bad. You get used to it after you've been wrong a few times. Cardanic joint is used, but that is not what it's supposed to be. It's supposed to be called a cardan joint, which to me, I speak English, just sounds wrong. But there you go. Or universal joint. Every universal joint I've seen has looked like this. But if it moves in all 3 axes at the same time, it's called a cardan joint. So that's what this is. That's a cardan joint. And I wanted to demonstrate the hand and show that it's possible. Because the robot people, as soon as you say it has a hydraulic cylinder in it, they go, nah, that's not going to work. So I wanted to make it out of plastic just to show that it works and that the hand has the range of motion and dexterity, mobility of a real human hand. And the interesting thing is, if it's going to be made out of printed 3D plastic, you don't have to bolt all the parts together. You can combine all the parts. And unfortunately, and I'll go off into SketchUp and show you some of these dimensions. While these kind of dimensions are possible, I mean, you got to remember, if this distance from here to here is 4 millimeters, you can imagine that this distance from here to here is like 0.6 millimeters. And that kind of size in plastic is not going to work. It's too small. And so I needed to make this bigger. I thought I could just make it bigger, but everything is so squeezed together. Once you start enlarging stuff, it completely changes the hand. So I've got to redo the whole hand to get everything to fit. That's what has been taking some time. And we'll look at some stuff in SketchUp. All right, and so you can see with 3D printing that while, and I think this hand is beautiful. Of course, I created it, so I always think it's beautiful. And I changed the opacity of some of the structures so you can see through them, so you can see what's going on. Like you can see that these fingers are bent over, and the reason why they're bent over is because these hydraulic cylinders, this one has pulled down and this one has pushed up, and it swung the finger down because I wanted a hand to be sort of showing off this cardan joint and that cardan joint and this hydraulic cylinder. In 3D printing, all of this can be combined together. And in order for them to 3D print, well, one thing I wanted to show you was in the metal hand, you have metal on metal where these things are moving, and that's going to tear up. And so what I did in order to have that not do that is in the metal structures, I made them purple. There is the polyacetal bushing bearings. It's a polymer of acetal plus polytetrafluoroethylene Teflon particles in it, so that you don't have metal rubbing on metal. None of that is necessary in the plastic version for two reasons. Number one, it's not a hand that's going to be someone using it for 2 or 3 years. Secondly, it's just to show that the hand can be made. And thirdly, the plastic can rub on the plastic. That's not going to be a big problem. So it has these bolts, it has these small parts, and it has these bushing bearings. None of this is needed in the plastic version. And each of the parts of it have to be created as a step file. And I have, well, here, I'll show you this. I went out, you can get these bolts in Fusion. You can get the bolts and download them from McMaster Carr in Fusion as step files, and you can create exact proper sizes of the head of the bolt and the nut and the hex socket nut bolts. And these are just some bolts that I'm just showing that so you can do that. And I put those in the drawing, and you can actually, in the drawings, you can pull in where these bolts are threaded, really actually threaded. But the drawing program will clog up if you have these as real threads, because it has to draw them. So these are kind of phaco threads. And I didn't thread it all the way to the back. That's the way the bolts are available. You got to remember that this is 1.4 millimeters in diameter and it's 6 millimeters long. They arrive completely threaded. Again, I didn't do that because it's too much drawing for the central processing unit. And over here, I just showed a graph of that I prepared of some of the parts of the fingers, just the fingers. So you see, I've got to make an individual step file for each of these proximal phalanges, 5 of them. And then there's the middle phalanges, 4 of them. The thumb doesn't have a middle phalange. And then the distal phalange, and that's step files for all of that. And over here you can see this is the plastic version. Now the plastic version, it just winds up being bigger to get all these parts in there. But these are the actual real parts in the plastic hand. Let's see here, we'll get a view where we can see it. So that's the distal phalange, the middle phalange, and the proximal phalange. There's not nearly as many bolts as there was, because this pink, I have it as a different color, but this is all actually one part. It's all one plastic part. These are some little rollers for these ligaments. And these little spindles keep these ligaments where they're supposed to be. And I actually have put in there, like, this is the middle phalange of the middle finger, MM. And this is the middle phalange of the ring finger. And that's what's going on there. And that's part of the drawing. This is the proximal phalange of the index finger, proximal phalange of the middle finger. So that's what's going on there, and that's plastic. The other thing I did was these hydraulic cylinders are now 8 millimeters of inside diameter. I feel like the hydraulic cylinders that I had are just too small. And I wanted to show you, here's the thumb. So see, I'm still working on the thumb. This is the hand. You'll notice that all these fingers are slightly different size. The little finger, ring finger, middle finger, index finger. I obtained these values by simply measuring the size of my own hand. And this distance is about 5.2 inches in the larger hand made for plastic printing. It's just how it's going to work out. And this is the frame. This frame can be one complete plastic part instead of all these parts that are bolted together when it's made out of alloy stainless steel. And I'm working on the thumb. And of course, when I make these YouTubes, just why not? I like to put in what is being shown to us on the computer from Bing. It's a Microsoft thing. Let's see what Bing is showing us. This is the Thousand Islands in the St. Lawrence River. So this is either Canada or America. And so that's what Bing is showing us. I don't know. I guess this would be all right as long as you bought enough groceries. I don't, you know, does this have utilities like water and stuff? I don't know. But here's another little house on a little more land. And we're just taking a look. I think it's kind of pretty. The other thing I like, let's see, we'll go. Thank you, Bing. I do like to also add this. I try to put a poster in my YouTubes. I asked the little mannequins if they would hold it. They grabbed some arms from the robot storage area where the robot people will say, your hand design is completely impossible, because I wanted to have these 4 specifications. One is for a human mimicking hand that people would care about. It's the same size as a normal hand. It can be a power hand. That is, the hand can lift up 200-pound weight. It has to be a dexterity hand where it can do what a human being can do. Write with a pencil, pick up a toothpick. It's also built in a way where it will keep working for years without having to keep replacing parts. My son tells me that all of the different Greek, he's a classical scholar, the Greek gods had properties and features. One of the goddesses was Cassandra, who was given the ability to see the future, but they always had some limitation on them. And Cassandra was given the ability to see the future, but her limitation was no one would believe her. I think that's a cool thought. Anyway, I put these 4 out on LinkedIn. I wish I knew, but nobody used to talk about the hand this way at all. Now, if you look at the hands on LinkedIn, they talk about how much it can lift up. They can talk about what it can do. And they show how the parts can, anyway, it's just interesting. I do have a YouTube channel, and I have a website. Here's the website, Piston Robot. And you go to the menu, and then you go discussions about a robot, and then you go to give the robot a hand. And that's where all the stuff is that I'm talking about. I always want to put this in. Any physically real object has the potential to hurt somebody. If you are managing a physically real item, my suggestion is to manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it in that way, it is my advice, do not create it as a physically real item. Okay, and while I like KeyShot because it's so pretty, some things are easier to show in SketchUp. We'll go over to SketchUp. And now we're inside SketchUp. I just find SketchUp easier to work with, for me. This is times 10 scale. And the reason why, okay, so we're measuring in millimeters. The reason why in times 10 scale is with the SketchUp, let me show you the hidden geometry. See what it puts in there? This is because it's a polygon-based drawing program, and each of these is tiny little triangles. And if you get the item small enough inside of SketchUp, you get millions and millions of tiny triangles, and SketchUp finds that it can't really work with it, and it gets messed up. And so very frequently, if you'll just multiply it times 10 for purposes of working with it, like see now this is not 4 millimeters, it's 44 millimeters, but it's really 4 millimeters, and the step files are the right size. But I'm showing it for purposes of showing times 10 because SketchUp works better. And so don't let that trouble you. And this is the hand. Now, these are these little bolts that I created that are in a variety of places. Now, another thing that okay, so here is the original cardan joint bolted together of alloy 2205 alloy stainless steel with spacers in there. This is the new one. You can see down below I was able to combine these two cardan joints into one cardan joint, and the thickness of this wall from 2205 alloy stainless steel is 0.7 millimeters. And for example, we can go here and turn the area into inches squared, and we can look at this. Okay, and this is showing us that this is 1.26 square inches, but you have to, since we're times 10, you have to divide it by 100. So it's 0.0126. Or to show you, I can go get the proper size. Let's do that real quick. So again, we're measuring length in millimeters, and we can go take a look at this this phalange, and it's 4 millimeters, 4.4 millimeters, and this is 4.4 millimeters, so it's sort of square. And we can go over here to the original 2205 alloy stainless steel part and drill down on it. And I don't do creation. This has to be created with CNC machining. So there's the part, and it has 7.8 millimeters squared, but we can switch this to inches in 4 places. So it's 0.0122 square inches. So the yield strength of 2205 alloy stainless steel is 50,000 pounds per square inch. So 0.0122 times 50, 1, 2, 3. Okay, so you could pull on this with 610 pounds of force. 610 pounds of force. And again, the recommendation for the bending strength for this to bend out that way is 1/2 of the tensile strength. So in order to bend this out that way, you would have to push on it with 310 pounds of force. And the only thing I can say to that is, let's do this in inches, is this thing is 4/10 of an inch long. Now, I was at Duke undergraduate and in chemistry, graduated with honors, but I had enough time to do philosophy courses. And we had philosophy reading that we had to read. And this person was making a philosophy point of how language changes the way you think about things, so that certain thoughts aren't had by certain cultures because their language doesn't work that way. And the example he gave was the statement, all mushrooms are poisonous, but I don't believe it. And he said, in the English language, in Western culture, you're not allowed to say that. You're not allowed to say that you are saying something is true, but you don't believe that it's true. You're not allowed to do that. I always thought that was like, cool. So this is, again, 2/100ths of an inch thick, and 1 point is not even a 1/2 inch long, and you can put 600 pounds of force on it. That to me is very close to all mushrooms are poisonous, but I don't believe it. It's just like, that can't be true. But the point I'm making, when you want to make it out of alloy stainless steel, I guess it's just a demonstration of just how strong alloy stainless steel is. we can go over here and see what happens when we make it out of plastic. And the problem with plastic is you can't have a wall that's 7/10 of a millimeter thick in printed plastic. That is not going to work. And so this is the new one, and the new one is different in that okay, so we'll go back over here. The distance here, thickness of this wall is 1.4 millimeters. That apparently is possible with PETG 3D printed plastic. And this, I also thought, since this is just a demonstration, and I'm probably, I mean, we'll see, almost surely I'm going to be paying for this. I decided I need to use bolts that are available. So this bolt is 10 millimeters. So the original one, the bolts that I chose, because they're pretty and they work and they fit together right, these bolts are 8.1 millimeters. And they also have this shortened head length and shortened nut length. And what I discovered when I went over and looked at parts that are available for an M1.2 bolt, they do have the shortened head length, but they do not have what they call the thin or low profile nylon insert lock. I did find nylon insert lock nuts of 1.2 M1.2 bolts, but they're not low profile. And so these change altered how it goes together. And you can see that all of these parts here were bolted on to the metal, but they're not bolted on over here. It's all one piece. Like, for example, this is bolted to that. That's still bolted there, but this is bolted to that, and this is bolted to this. And over here, if you go to the part, that's all one part. That's all of that is put together with PETG plastic. This whole thing, all one piece. It's all one step file. And down here is what allows the joint to work. And we can look at that in areas in inch. Okay, so that's inches. So that comes out to be 0.0025 square inches. So the tensile strength of PETG is 7,000 pounds per square inch. So 0.0025 times 7,000 is 17 pounds. So you can put 17 pounds of force on this, except that to shear it, it's half that. So it's about 8 pounds, but there's two of them. So that means you can put 17 pounds of force on this finger if it's made out of PETG plastic. And again, this is just to demonstrate that the hand can be made, but it means to me that it's strong enough that it's not going to break as soon as you start handling it. And I've got the view set. All right, so you can see everything now, and we'll close this out. So in order for this cardan joint to work, to give multi-axis movement, you can see that these little pins right here allow this to go back and forth that way, these little pins. And then if the whole thing wants to go back and forth this way, it can't do that with these, but this whole entire block will move. So okay, so we've got this and that. Okay. So if we wanted it to move in one axis, we can select this rotational point and it moves like this. Okay. If we wanted it to move the other way, we don't select this one, we select that. And that whole thing will move this way. And that's what makes it a cardan joint. And in terms of 3D printing, okay, so this is what allows it to move this way. You'll see that that whole entire part up there is moving. And that's how the cardan joint works. So in order to 3D print this, I have to print this, that square right there, and I'll get a step file for each of these. So there's two of these. So here's one right there. There's the other one right there. Then there's one of these over here and one of these over there. And then they are inside of this. Okay. And inside of this, to stabilize it, I put these. Now this material here is just PEEK, polyether ether ketone tubing, 2 millimeters internal diameter, 3 millimeters outside diameter, to help to try to stabilize this thing. So now we can go over here. So, you know, that's 1, 2, 3, 4, 5, 6, 7, 8 parts just for this cardan joint, and 8 parts for that cardan joint, plus the piston rod, plus the hydraulic cylinder, plus 8 parts down here and 8 parts down there, and this. And when you go over here, you can see with 5 fingers. Okay, and I'm going to give you step files for each one of these parts. But and you can see here, if you look at the thumb is not done yet. Now I have to, this is a little bit difficult, but you can see, okay, so there's my fingernail right there. Okay, and my fingernail is pointed out this way. And as I swing my hand, my thumb around, okay, my fingernail that was pointed off to my left here is now pointing directly away from me. And what that means is the human hand, the thumb of the human hand can rotate. The other finger, so if I take my finger here and I try to rotate it, it won't, it's a little bit flexible because I have flexible joints, but it won't really rotate. Whereas the thumb, see my fingernails pointed straight down? The thumb now is pointed over here. The thumb can rotate. That's what this joint is. This is the thumb. It has the same metacarpal phalangeal joint as the others do, but it's also got this ability to rotate. And in addition to that, the human thumb can go from right in front of the palm all the way out over here where it's out of the way. That's what these three, well, let's see here, how many is there? That's what these 2 hydraulic cylinders do, plus this support structure, and they're all cardan joints. And then the other thing that the hand can do, you can see, notice that my metacarpal phalangeal joints are lined up with my wrist, but I can make my wrist go forward. And I can make, well, let me rephrase it. I can take the metacarpal phalangeal joints and make them go forward compared to my wrist, and make them go backward compared to my wrist. And I can move them off. I can take my metacarpal phalangeal joint area and move it that way or that way. And that is what these set of cardan joints is all about. And all of these, I have to bring them up to the 8 millimeter inside diameter, and I have to bring them up to the larger size of cardan joint. None of that is just work, but I thought I would make just a note to let you see what's going on and what has happened. And enjoy, and I'll keep you informed.